Halley's Comet. Halley's Comet is the only known short-period comet that is consistently visible to the naked eye from Earth, appearing every 72 to 80 years. It last appeared in the inner parts of the Solar System in 1986 and will next appear in mid-2061. Officially designated 1P/Halley, it is also commonly called Comet Halley, or sometimes simply Halley. Halley's periodic returns to the inner solar system have been observed and recorded by astronomers around the world since at least 240 BC, but it was not until 1705 that the English astronomer Edmund Halley understood that these appearances were reappearances of the same comet. As a result of this discovery, the comet is named after Halley. During its 1986 visit to the inner solar system, Halley's Comet became the first comet to be observed in detail by spacecraft, providing the first observational data on the structure of a comet nucleus and the mechanism of coma and tail formation. These observations supported a number of long-standing hypotheses about comet construction, particularly Fred Whipple's dirty snowball model, which correctly predicted that Halley would be composed of a mixture of volatile ices, such as water, carbon dioxide, ammonia, and dust. The missions also provided data that substantially reformed and reconfigured these ideas. For instance, it is now understood that the surface of Halley is largely composed of dusty, non-volatile materials, and that only a small portion of it is icy. Pronunciation. Comet Halley is usually pronounced /Halley/ rhyming with valley, or sometimes /Halley/ rhyming with daily. As to the surname Halley, Colin Ronan, one of Edmund Halley's biographers, preferred /Halley/ rhyming with Crawley. Spellings of Halley's name during his lifetime included Haley, 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 Halley, Hawley, and Hawley, so its contemporary pronunciation is uncertain, but the version rhyming with valley seems to be preferred by current bearers of the surname. Computation of orbit. Halley was the first comet to be recognized as periodic. Until the Renaissance, the philosophical consensus on the nature of comets, promoted by Aristotle, was that they were disturbances in Earth's atmosphere. This idea was disproven in 1577 by Tycho Brahe, who used parallax measurements to show that comets must lie beyond the Moon. Many were still unconvinced that comets orbited the Sun, and assumed instead that they must follow straight paths through the solar system. In 1687, Sir Isaac Newton published his Philosophiae Naturalis Principia Mathematica, in which he outlined his laws of gravity and motion. His work on comets was decidedly incomplete. Although he had suspected that two comets that had appeared in succession in 1680 and 1681 were the same comet before and after passing behind the Sun, he was later found to be correct. See Newton's comet. He was initially unable to completely reconcile comets into his model. Ultimately, it was Newton's friend, editor and publisher, Edmund Halley, who, in his 1705 synopsis of the astronomy of comets, used Newton's new laws to calculate the gravitational effects of Jupiter and Saturn on cometary orbits. Having compiled a list of 24 comet observations, he calculated that the orbital elements of a second comet that had appeared in 1682 were nearly the same as those of two comets that had appeared in 1531, observed by Petrus Apianus, and 1607, observed by Johannes Kepler. Halley thus concluded that all three comets were, in fact, the same object returning about every 76 years, a period that has since been found to vary between 72 and 80 years. After a rough estimate of the perturbations the comet would sustain from the gravitational attraction of the planets, he predicted its return for 1758. While he had personally observed the comet around perihelion in September 1682, Halley died in 1742 before he could observe its predicted return. Halley's prediction of the comet's return proved to be correct, although it was not seen until the 25th of December 1758, by Johann Georg Palitzsch, a German farmer and amateur astronomer. It did not pass through its perihelion until the 13th of March 1759, the attraction of Jupiter and Saturn having caused a retardation of 618 days. This effect was computed before its return, with a 1-month error to the 13th of April, by a team of 3 French mathematicians, Alexis Clairaut, Joseph Lalande, and Nicole Rennes-Lepert. The confirmation of the comet's return was the first time anything other than planets had been shown to orbit the Sun. It was also one of the earliest successful tests of Newtonian physics, and a clear demonstration of its explanatory power. The comet was first named in Halley's honor by French astronomer Nicolas Louis de Lacaille in 1759. Some scholars have proposed that first-century Mesopotamian astronomers already had recognized Halley's comet as periodic. This theory notes a passage in the Babylonian Talmud, Tractate Horeo, that refers to a star which appears once in 70 years that makes the captains of the ship Sir. Others doubt this idea based on historical considerations about the exact timing of this alleged observation, and suggest it refers to other astronomical phenomena. Researchers in 1981 attempting to calculate the past orbits of Halley by numerical integration starting from accurate observations in the 17th and 18th centuries could not produce accurate results further back than 837 owing to a close approach to Earth in that year. It was necessary to use ancient Chinese comet observations to constrain their calculations. Orbit and origin. Halley's orbital period has varied between 74 and 80 years since 240 BC. Its orbit around the Sun is highly elliptical, with an orbital eccentricity of 0.967, with 0 being a circle and 1 being a parabolic trajectory. The perihelion, the point in the comet's orbit when it is nearest the Sun, is 0.590, 88 million km. This is between the orbits of Mercury and Venus. Its aphelion, or farthest distance from the Sun, is 5.2 billion km, roughly the orbital distance of Pluto. Unlike the overwhelming majority of objects in the Solar System, Halley's orbit is retrograde. It orbits the Sun in the opposite direction to the planets, or clockwise from above the Sun's north pole. The orbit is inclined by 18 degrees to the ecliptic, with much of it lying south of the ecliptic. Because it is retrograde, the true inclination is 162 degrees. Owing to the retrograde orbit, it has one of the highest velocities relative to the Earth of any object in the Solar System. The 1910 passage was at a relative velocity of 70.56 km per second, 157,800 miles per hour. Because its orbit comes close to Earth's in two places, Halley is associated with two meteor showers, the E2 Aquariids in early May, and the Orionids in late October. Halley is classified as a periodic or short-period comet, one with an orbit lasting 200 years or less. This contrasts it with long-period comets, whose orbits last for thousands of years. Periodic comets have an average inclination to the ecliptic of only 10 degrees, and an orbital period of just 6.5 years, so Halley's orbit is atypical. Most short-period comets, those with orbital periods shorter than 20 years and inclinations of 30 degrees or less, are called Jupiter family comets. Those resembling Halley, with orbital periods of between 20 and 200 years and inclinations extending from 0 to more than 90 degrees, are called Halley-type comets. As of 2024, 105 Halley-type comets have been observed, compared with 816 identified Jupiter family comets. The orbits of the Halley-type comets suggest that they were originally long-period comets whose orbits were perturbed by the gravity of the giant planets and directed into the inner solar system. If Halley was once a long-period comet, it is likely to have originated in the Oort cloud, a sphere of cometary bodies around 20,000 to 50,000 O from the Sun. Conversely, the Jupiter family comets are generally believed to originate in the Kuiper belt, a flat disk of icy debris between 30 O, Neptune's orbit, and 50 O from the Sun, in the scattered disk. Another point of origin for the Halley-type comets was proposed in 2008, when a trans-Neptunian object with a retrograde orbit similar to Halley's was discovered, 2008 KV42, whose orbit takes it from just outside that of Uranus to twice the distance of Pluto. It may be a member of a new population of small solar system bodies that serves as the source of Halley-type comets. Halley has probably been in its current orbit for 16,000 to 200,000 years, although it is not possible to numerically integrate its orbit for more than a few tens of apparitions, and close approaches before 837 AD can only be verified from recorded observations. The non-gravitational effects can be crucial. As Halley approaches the Sun, it expels jets of sublimating gas from its surface, which knock it very slightly off its orbital path. These orbital changes cause delays in its perihelion passage of 4 days on average. In 1989, Boris Kirikov and Witold Vexlave have performed an analysis of 46 apparitions of Halley's comet taken from historical records and computer simulations, which showed that its dynamics were chaotic and unpredictable on long time scales. Halley's projected dynamical lifetime is estimated to be about 10 million years. The dynamics of its orbit can be approximately described by a two-dimensional symplectic map, known as the Kepler map, a solution to the restricted three-body problem for highly eccentric orbits. Based on records from the 1910 apparition, David Hughes calculated in 1985 that Halley's nucleus has been reduced in mass by 80 to 90% over the last 2,000 to 3,000 revolutions, and that it will most likely disappear completely after another 2,300 perihelion passages. More recent work suggests that Halley will evaporate, or split in two, within the next few tens of thousands of years, or will be ejected from the solar system within a few 100,000 years. Structure and composition. The Giotto and Vega missions gave planetary scientists their first view of Halley's surface and structure. The nucleus is a conglomerate of ices and dust, often referred to as a dirty snowball. Like all comets, as Halley nears the Sun, its volatile compounds, those with low boiling points, such as water, carbon monoxide, carbon dioxide and other ices, begin to sublimate from the surface. This causes the comet to develop a coma, or atmosphere, at distances up to 230,000 kilometers, 140,000 miles, from the nucleus. Sublimation of this dirty ice releases dust particles, which travel with the gas away from the nucleus. Gas molecules in the coma absorb solar light and then re-radiate it at different wavelengths, a phenomenon known as fluorescence, whereas dust particles scatter the solar light. Both processes are responsible for making the coma visible. As a fraction of the gas molecules in the coma are ionized by the solar ultraviolet radiation, pressure from the solar wind, a stream of charged particles emitted by the Sun, pulls the coma's ions out into a long tail, which may extend more than 100 million kilometers into space. Changes in the flow of the solar wind can cause disconnection events, in which the tail completely breaks off from the nucleus. Despite the vast size of its coma, Halley's nucleus is relatively small, barely 15 kilometers, 9.3 miles, long, 8 kilometers, 5.0 miles, wide and perhaps 8 kilometers, 5.0 miles, thick. Based on a reanalysis of images taken by the Giotto and Vega spacecraft, Lamy et al. Determined an effective diameter of 11 kilometers, 6.8 miles. Its shape has been variously compared to that of a peanut, a potato, or an avocado. Its mass is roughly 2.2 times 1014 kilograms, with an average density of about 0.55 grams per cubic centimeter, 0.32 ounces/Cu. The low density indicates that it is made of a large number of small pieces, held together very loosely, forming a structure known as a rubble pile. Ground-based observations of coma brightness suggested that Halley's rotation period was about 7.4 days. Images taken by the various spacecraft, along with observations of the jets and shell, suggested a period of 52 hours. Given the irregular shape of the nucleus, Halley's rotation is likely to be complex. The flyby images revealed an extremely varied topography, with hills, mountains, ridges, depressions, and at least one crater. Halley's day side, the side facing the Sun, is far more active than the night side. spacecraft. Observations showed that the gases ejected from the nucleus were 80% water vapor, 17% carbon monoxide and 3 to 4% carbon dioxide, with traces of hydrocarbons, although more recent sources give a value of 10% for carbon monoxide and also include traces of methane and ammonia. The dust particles were found to be primarily a mixture of carbon, hydrogen, oxygen, nitrogen, CHON, compounds common in the outer solar system, and silicates, such as are found in terrestrial rocks. The dust particles ranged in size down to the limits of detection, 0.001 m. The ratio of deuterium to hydrogen in the water released by Halley was initially thought to be similar to that found in Earth's ocean water, suggesting that Halley-type comets may have delivered water to Earth in the distant past. Subsequent observations showed Halley's deuterium ratio to be far higher than that found in Earth's oceans, making such comets unlikely sources for Earth's water. Giotto provided the first evidence in support of Fred Whipple's dirty snowball hypothesis for comet construction. Whipple postulated that comets are icy objects warmed by the sun as they approach the inner solar system, causing ices on their surfaces to sublime, change directly from a solid to a gas, and jets of volatile material to burst outward, creating the coma. Giotto showed that this model was broadly correct, though with modifications. Halley's albedo, for instance, is about 4%, meaning that it reflects only 4% of the sunlight hitting it, about what one would expect for coal. Thus, despite astronomers predicting that Halley would have an albedo of about 0.17, roughly equivalent to bare soil, Halley's comet is in fact pitch black. The dirty ice is on the surface sublime at temperatures between 170 K, -103 degrees Celsius, in sections of higher albedo to 220 K, -53 degrees Celsius. At low albedo, Vega 1 found Halley's surface temperature to be in the range 300 to 400 K, 27 to 127 degrees Celsius. This suggested that only 10% of Halley's surface was active, and that large portions of it were coated in a layer of dark dust that retained heat. Together, these observations suggested that Halley was in fact predominantly composed of non-volatile materials, and thus more closely resembled a snowy dirt ball than a dirty snowball. History. Before 1066. The first certain appearance of Halley's comet in the historical record is a description from 240 BC, in the Chinese chronicle records of the Grand Historian or Shiji, which describes a comet that appeared in the east and moved north. The only surviving record of the 164 BC apparition is found on two fragmentary Babylonian tablets, which were rediscovered in August 1984 in the collection of the British Museum. The apparition of 87 BC was recorded in Babylonian tablets which state that the comet was seen day beyond day for a month. This appearance may be recalled in the representation of Tigranes the Great, an Armenian king who is depicted on coins with a crown that features, according to Gurzadian and R. Vardanyan, a star with a curved tail may represent the passage of Halley's comet in 87 BC. Gurzadian and Vardanyan argue that Tigranes could have seen Halley's comet when it passed closest to the Sun on August 6 in 87 BC, as the comet would have been a most recordable event. For ancient Armenians it could have heralded the new era of the brilliant King of Kings. The apparition of 12 BC was recorded in the Book of Han by Chinese astronomers of the Han dynasty who tracked it from August through October. It passed within 0.160 of Earth. According to the Roman historian Cassius Dio, a comet appeared suspended over Rome for several days, portending the death of Marcus Vipsanius Agrippa in that year. Halley's appearance in 12 BC, only a few years distant from the conventionally assigned date of the birth of Jesus Christ, has led some theologians and astronomers to suggest that it might explain the biblical story of the Star of Bethlehem. There are other explanations for the phenomenon, such as planetary conjunctions, and there are also records of other comets that appeared closer to the date of Jesus' birth. If Yehoshua ben Hananiah's reference to a star which arises once in 70 years and misleads the sailors refers to Halley's comet, he can only have witnessed the 66 AD appearance. Another possible report comes from Jewish historian Josephus, who wrote that in 66 AD the signs were so evident, and did so plainly foretell their future desolation. There was a star resembling a sword, which stood over the city, and a comet, that continued a whole year. This portent was in reference to the city of Jerusalem and the First Jewish-Roman War. The 141 AD apparition was recorded in Chinese chronicles. The 374 AD and 607 approaches each came within 0.090 of Earth. The 451 AD apparition was said to herald the defeat of Attila the Hun at the Battle of Chalons. The 684 AD apparition was reported in Chinese records as the Broom Star. The 760 AD apparition was recorded in the Zhuangnan Chronicles entry for year 1071 SE, May 760 AD, calling it a white sign. The year 1071, AD 759-760. In the month of Eeyore, May, a white sign was seen in the sky, before early twilight, in the northeast, in the zodiac which is called Aries, to the north from these three stars in it, which are very shining. And it resembled in its shape a broom, and the sign itself remained for 15 nights, until dawn of the Feast of Pentecost. In 837 AD, Halley's comet may have passed as close as 0.03 astronomical units, 2.8 million miles, 4.5 million kilometers, from Earth, by far its closest approach. Its tail may have stretched 60 degrees across the sky. It was recorded by astronomers in China, Japan, Germany, the Byzantine Empire, and the Middle East. Emperor Louis the Pious observed this appearance and devoted himself to prayer and penance, fearing that by this token a change in the realm and the death of a prince are made known. In 912 AD, Halley is recorded in the Annals of Ulster, which states a dark and rainy year. A comet appeared. 1066. In 1066, the comet was seen in England and thought to be an omen. Later that year Harold II of England died at the Battle of Hastings and William the Conqueror claimed the throne. The comet is represented on the Bayeux Tapestry and described in the Tigili as a star. Surviving accounts from the period describe it as appearing to be 4 times the size of Venus, and shining with a light equal to a quarter of that of the Moon. Halley came within 0.100 of Earth at that time. This appearance of the comet is also noted in the Anglo-Saxon Chronicle. Aylmer of Malmesbury may have seen Halley in 989 and 1066, as recorded by William of Malmesbury not long after. A comet, portending, they say, a change in governments, appeared, trailing its long flaming hair through the empty sky, concerning which there was a fine saying of a monk of our monastery called Ethelmer. Crouching in terror at the sight of the gleaming star, "You've come, have you?" he said. "You've come, you source of tears to many mothers. It is long since I saw you, but as I see you now you are much more terrible, for I see you brandishing the downfall of my country." The Irish Annals of the Four Masters recorded the comet as a star appeared on the 7th of the calends of May, on Tuesday after Little Easter, than whose like the brilliance or light of the moon was not greater, and it was visible to all in this manner till the end of 4 nights afterwards. Chaco Native Americans in New Mexico may have recorded the 1066 apparition in their petroglyphs. The Italo-Byzantine Chronicle of Lupus the Protospathaurios mentions that a comet star appeared in the sky in the year 1067. The chronicle is erroneous, as the event occurred in 1066, and by Robert he means William. The Emperor Constantine Ducas died in the month of May, and his son Michael received the empire. And in this year there appeared a comet star, and the Norman Count Robert fought a battle with Harold, king of the English, and Robert was victorious and became king over the people of the English. 1145 to 1378. The 1145 apparition may have been recorded by the monk Edwine. According to legend, Genghis Khan was inspired to turn his conquests toward Europe by the westward seeming trajectory of the 1222 apparition. In Korea, the comet was reportedly visible during the daylight on the 9th of September 1222. The 1301 apparition was visually spectacular, and may be the first that resulted in convincing portraits of a particular comet. The Florentine chronicler Giovanni Villani wrote that the comet left great trails of fumes behind, and that it remained visible from September 1301 until January 1302. It was seen by the artist Giotto di Bondone, who represented the Star of Bethlehem as a fire-colored comet in the Nativity section of his Arena Chapel cycle, completed in 1305. Giotto's depiction includes details of the coma, a sweeping tail, and the central condensation. According to the art historian Roberto Olsen, it is much more accurate than other contemporary descriptions, and was not equaled in painting until the 19th century. Olsen's identification of Halley's comet in Giotto's adoration of the Magi is what inspired the European Space Agency to name their mission to the comet Giotto, after the artist. Halley's 1,378 appearances recorded in the Annales Mediolanenses as well as in East Asian sources. 1456. In 1456, the year of Halley's next apparition, the Ottoman Empire invaded the Kingdom of Hungary, culminating in the Siege of Belgrade in July of that year. In a papal bull, Pope Calixtus III ordered special prayers be said for the city's protection. In 1470, the humanist scholar Bartolomeo Platina wrote in his Lives of the Popes that, a hairy and fiery star having then made its appearance for several days, the mathematicians declared that there would follow grievous pestilence, dearth and some great calamity. Calixtus, to avert the wrath of God, ordered supplications that if evils were impending for the human race he would turn all upon the Turks, the enemies of the Christian name. He likewise ordered, to move God by continual entreaty, that notice should be given by the bells to call the faithful at midday to aid by their prayers those engaged in battle with the Turk. Platina's account is not mentioned in official records. In the 18th century, a Frenchman further embellished the story, in anger at the Church, by claiming that the Pope had excommunicated the comet, though this story was most likely his own invention. Halley's apparition of 1456 was also witnessed in Kashmir and depicted in great detail by Srivara, a Sanskrit poet and biographer to the sultans of Kashmir. He read the apparition as a cometary portent of doom foreshadowing the imminent fall of Sultan Zayn al-Abidin, AD 1418/1420–1470. After witnessing a bright light in the sky which most historians have identified as Halley's comet, Tsar Yacob, Emperor of Ethiopia from 1434 to 1468, founded the city of Debre Berhan, Tr. City of Light, and made it his capital for the remainder of his reign, 1531 to 1759. Petrus Apianus and Girolamo Fracastoro described the comet's visit in 1531, with the former even including graphics in his publication. Through his observations, Apianus was able to prove that a comet's tail always points away from the sun. In the Sikh scriptures of the Guru Granth Sahib, the founder of the faith Guru Nanak makes reference to a long star that has risen at Anj 1110, and it is believed by some Sikh scholars to be a reference to Halley's appearance in 1531. Halley's periodic returns have been subject to scientific investigation since the 16th century. The three apparitions from 1531 to 1682 were noted by Edmund Halley, enabling him to predict it would return. One key breakthrough occurred when Halley talked with Newton about his ideas of the laws of motion. Newton also helped Halley get John Flamsteed's data on the 1682 apparition. By studying data on the 1531, 1607, and 1682 comets, he came to the conclusion these were the same comet, and presented his findings in 1696. One difficulty was accounting for variations in the comet's orbital period, which was over a year longer between 1531 and 1607 than it was between 1607 and 1682. Newton had theorized that such delays were caused by the gravity of other comets, but Halley found that Jupiter and Saturn would cause the appropriate delays. In the decades that followed, more refined mathematics would be worked on, notable by Paris Observatory. The work on Halley also provided a boost to Newton and Kepler's rules for celestial motions. See also Computation of Orbit. 1835. At Markrey Observatory in Ireland, Edward Joshua Cooper used a Coquoix of Paris lens telescope with an aperture of 340 mm (13.3 in) to sketch Halley's comet in 1835. The same apparition was sketched by German astronomer Friedrich Wilhelm Bessel. Observations of streams of vapor prompted Bessel to propose that the jet forces of evaporating material could be great enough to significantly alter a comet's orbit. An interview in 1910, of someone who was a teenager at the time of the 1835 apparition had this to say: when the comet was first seen, it appeared in the western sky, its head toward the north and tail towards the south, about horizontal and considerably above the horizon and quite a distance south of the sun. It could be plainly seen directly after sunset every day, and was visible for a long time, perhaps a month. They go on to describe the comet's tail as being more broad and not as long as the comet of 1843 they had also witnessed. Famous astronomers across the world made observations starting August 1835, including Struve at Dorpat Observatory, and Sir John Herschel, who made observations from the Cape of Good Hope. In the United States, telescopic observations were made from Yale College. The new observations helped confirm early appearances of this comet, including its 1456 and 1378 apparitions. At Yale College in Connecticut, the comet was first reported on the 31st of August 1835 by astronomers D. Olmsted and E. Loomis. In Canada, reports were made from Newfoundland and also Quebec. Reports came in from all over by later 1835, and often reported in newspapers of this time in Canada. Several accounts of the 1835 apparition were made by observers who survived until the 1910 return, where increased interest in the comet led to their being interviewed. The time to Halley's return in 1910 would be only 74.42 years, one of the shortest known periods of its return, which is calculated to be as long as 79 years owing to the effects of the planets. At Paris Observatory, Halley's Comet 1835 apparition was observed with Leribaud's telescope of 24.4 cm, 9.6 in, aperture by the astronomer François Arago. Arago recorded polarimetric observations of Halley, and suggested that the tail might be sunlight reflecting off a sparsely distributed material. He had earlier made similar observations of comet Tralles of 1819. 1910. The 1910 approach, which came into naked eye view around the 10th of April and came to perihelion on the 20th of April, was notable for several reasons. It was the first approach of which photographs exist, and the first for which spectroscopic data were obtained. Furthermore, the comet made a relatively close approach of 0.150, making it a spectacular sight. Indeed, on the 19th of May, Earth actually passed through the tail of the comet. One of the substances discovered in the tail by spectroscopic analysis was the toxic gas cyanogen, which led press to misquote the astronomer Camille Flammarion by stating he claimed that, when Earth passed through the tail, the gas would impregnate the atmosphere and possibly snuff out all life on the planet. Despite reassurances from scientists that the gas would not inflict harm on Earth, the damage had already been done, with members of the public panic buying gas masks and quack anti-comet pills. The comet added to the unrest in China on the eve of the Xinhai Revolution that would end the last dynasty in 1911. As James Hudson, a missionary in Sichuan province at the time, recorded, the people believe that it indicates calamity such as war, fire, pestilence, and a change of dynasty. In some places on certain days the doors were unopened for half a day, no water was carried, and many did not even drink water, as it was rumored that pestilential vapor was being poured down upon the earth from the comet. The 1910 visitation is also recorded as being the traveling companion of Hedley Churchward, the first known English Muslim to make the Hajj pilgrimage to Mecca. However, his explanation of its scientific predictability did not meet with favor in the Holy City. The comet was used in an advertising campaign of Le Bon Marché, a well-known department store in Paris. The comet was also fertile ground for hoaxes. One that reached major newspapers claimed that the Sacred Followers, a supposed Oklahoma religious group, attempted to sacrifice a virgin to ward off the impending disaster, but were stopped by the police. American satirist and writer Mark Twain was born on the 30th of November 1835, exactly 2 weeks after the comet's perihelion. In his autobiography, published in 1909, he said, "I came in with Halley's comet in 1835. It is coming again next year, and I expect to go out with it. It will be the greatest disappointment of my life if I don't go out with Halley's comet. The Almighty has said, no doubt, now here are these two unaccountable freaks, they came in together, they must go out together." Twain died on the 21st of April 1910, the day following the comet's subsequent perihelion. The 1985 fantasy film The Adventures of Mark Twain was inspired by the quotation. Halley's 1910 apparition is distinct from the Great Daylight Comet of 1910, which surpassed Halley in brilliance and was visible in broad daylight for a short period, approximately 4 months before Halley made its appearance. 1986. The 1986 apparition of Halley's comet was the least favorable on record. In February 1986, the comet and the Earth were on opposite sides of the Sun, creating the worst possible viewing circumstances for Earth observers during the previous 2,000 years. Halley's closest approach was 0.420. Additionally, increased light pollution from urbanization caused many people to fail in attempts to see the comet. With the help of binoculars, observation from areas outside cities was more successful. Further, the comet appeared brightest when it was almost invisible from the northern hemisphere in March and April 1986, with best opportunities occurring when the comet could be sighted close to the horizon at dawn and dusk, if not obscured by clouds. The approach of the comet was first detected by astronomers David C. Jewett and G. Edward Danielson on the 16th of October 1982 using the 5.1 meters Hale telescope at Mount Palomar and a CCD camera. The first visual observation of the comet on its 1986 return was by an amateur astronomer, Stephen James O'Meara, on the 24th of January 1985. O'Meara used a home-built 610mm, 24-in, telescope on top of Mauna Kea to detect the magnitude 19.6 comet. The first to observe Halley's comet with the naked eye during its 1986 apparition was Stephen Edberg, then serving as the coordinator for amateur observations at the NASA Jet Propulsion Laboratory, and Charles Morris on the 8th of November 1985. The 1986 apparition gave scientists the opportunity to study the comet closely, and several probes were launched to do so. The Soviet Vega 1 probe began returning images of Halley on the 4th of March 1986, captured the first ever image of its nucleus, and made its flyby on the 6th of March. It was followed by the Vega 2 probe, making its flyby on the 9th of March. On the 14th of March, the Giotto space probe, launched by the European Space Agency, made the closest pass of the comet's nucleus. There also were 2 Japanese probes, Suisei and Sokigaki. Unofficially, the numerous probes became known as the Halley Armada. Based on data retrieved by the largest ultraviolet space telescope of the time, Astron, in December 1985, a group of Soviet scientists developed a model of the comet's coma. The comet also was observed from space by the International Cometary Explorer, ICE. Originally launched as the International Sun-Earth Explorer 3, the spacecraft was renamed, and departed the Sun-Earth L1 Lagrangian point in 1982 in order to intercept the comet's 21P/Jacobinis inner and Halley. ICE flew through the tail of Halley's comet, coming within about 40.2 million km, 25.0 million mile, of the nucleus on the 28th of March 1986. 2 U.S. Space Shuttle missions, STS-51 and STS-61E, had been scheduled to observe Halley's comet from low Earth orbit. The STS-51 mission carried the shuttle-pointed tool for astronomy, Spartan Halley, satellite, also called the Halley's Comet Experiment Deployable, HCED. The mission to capture the ultraviolet spectrum of the comet ended in disaster when the Space Shuttle Challenger exploded in flight, killing all 7 astronauts on board. Scheduled for March 1986, STS-61E was a Columbia mission carrying the Astro 1 platform to study the comet, but the mission was cancelled following the Challenger disaster, and Astro 1 would not fly until late 1990 on STS-35, after 1986. On the 12th of February 1991, at a distance of 14.30, 2.14 times 109 kilometers, from the Sun, Halley displayed an outburst that lasted for several months. The comet released dust with a total mass of about 108 kilograms, which spread into an elongated cloud roughly 374,000 kilometers, 232,000 miles, by 269,000 kilometers, 167,000 miles, in size. The outburst likely started in December 1990, and then the comet brightened from about magnitude 25 to magnitude 19. Comets rarely show outburst activity at distances beyond 50 from the Sun. Different mechanisms have been proposed for the outburst, ranging from interaction with the solar wind to a collision with an undiscovered asteroid. The most likely explanation is a combination of two effects: the polymerization of hydrogen cyanide and a phase transition of amorphous water ice, which raised the temperature of the nucleus enough for some of the more volatile compounds on its surface to sublime. Halley was most recently observed in 2003 by three of the very large telescopes at Paranal, Chile, when Halley's magnitude was 28.2. The telescopes observed Halley, at the faintest and farthest any comet had ever been imaged, in order to verify a method for finding very faint trans-Neptunian objects. Astronomers are now able to observe the comet at any point in its orbit. On the 9th of December 2023, Halley's comet reached the farthest and slowest point in its orbit from the Sun when it was traveling at 0.91 km per second, 2,000 miles per hour, with respect to the Sun. 2061. The next perihelion of Halley's comet is predicted for the 28th of July 2061, when it will be better positioned for observation than during the 1985 to 1986 apparition, as it will be on the same side of the Sun as Earth. The closest approach to Earth will be 1 day after perihelion. It is expected to have an apparent magnitude of -0.3, compared with only +2.1 for the 1986 apparition. On the 9th of September 2060, Halley will pass within 0.980, 147 million kilometers, of Jupiter, and then on the 20th of August 2061 will pass within 0.05430, 8,120,000 kilometers, of Venus. 2134. Halley will come to perihelion on the 27th of March 2134. Then on the 7th of May 2134, Halley will pass within 0.0920, 13,800,000 kilometers, of Earth. Its apparent magnitude is expected to be -2.0. Apparitions. Halley's calculations enable the comet's earlier appearances to be found in the historical record. The following table sets out the astronomical designations for every apparition of Halley's comet from 240 BC, the earliest documented widespread sighting. In the designations, 1p/ refers to Halley's comet, the first periodic comet discovered. The number represents the year, with negatives representing BC. The letter-number combination indicates which it was of the comets observed for a given segment of the year, divided into 24 equal parts. The Roman numeral indicates which comet passed perihelion it was for a given year, while the lowercase letter indicates which comet it was for a given year overall. The perihelion dates farther from the present are approximate, mainly because of uncertainties in the modeling of non-gravitational effects. Perihelion dates of 1531 and earlier are in the Julian calendar, while perihelion dates 1607 and after are in the Gregorian calendar. The perihelion dates for some of the early apparitions, particularly before 837 AD, are uncertain by a couple of days. While Halley's comet usually peaks at around 0th magnitude, there are indications that the comet got considerably brighter than that in the past. 1p/1758 y11759 I1p/1835 p118 C1P/1909 R11910II 1909 C1P/1982 U119863 1982 I